Hello, my AP Chemers. We are talking about thermodynamics, and we had said that in order for a reaction to be spontaneous or thermodynamically favorable, there are two driving forces that affect that or that determine that, entropy and enthalpy. So let's start with entropy. Nature prefers the spread of matter, and so it prefers that our delta S would be positive. That's something that is favored. Meaning that the products would have more disorder and more randomness than the reactants. In terms of enthalpy, nature prefers exothermic processes, where delta H is negative. That's also a good thing. That's because nature prefers the spread of energy, and so if you have an exothermic process where you're having decreasing in potential energy, so your reactants are higher in energy than your products are more stable, lower in potential energy, and that difference in energy has been spread out to the surroundings. So that is also favorable. So if you have a reaction where delta S is positive, so you're increasing in entropy, and delta H is negative, so you're decreasing in enthalpy, that's great. That means that reaction is going to be spontaneous or thermodynamically favorable. Well, what if it was the opposite? What if the delta S was negative and the delta H was positive? Well, if delta S is negative, that's not favored by entropy, and if delta H is positive, that's not favored by enthalpy, and so in that case, that's definitely going to be non-spontaneous. That reaction will not occur without outside intervention. It's going to be not spontaneous. What if both of them were positive? Well, if delta S is positive, that's good, that's favored. If delta H is positive, that's not good, that's not favored. So now what? Or what if both of them are negative? Well, delta S being negative, that's not favored, and delta H negative, that is favored. So now what? So here, the entropy is saying, go, go, go. The enthalpy is saying, nope, you can't. And here it's the opposite. The entropy is saying, no, 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 don't go. And the delta H is saying, yes, go. So then what? So sometimes we can't really tell because one force is saying the reaction should go and one force is saying the reaction should not. So we can't tell if it's spontaneous or not. And so they came up with something called Gibbs free energy. It's completely made up. It is related actually to the delta S of the universe. So the second law of thermodynamics says that for a process to occur, the delta S of the whole universe, so that's the system and the surroundings together, needs to be positive, needs to be increasing. And so Gibbs free energy is related to that delta S of the universe. So Gibbs free energy, delta G, by definition is the available energy to do useful work. And what it's used for, it's a made up value. You can't really go to the lab and measure it, but you can calculate it if you have delta H and delta S. But what it's used for is to determine whether a reaction is thermodynamically favorable or not, whether it's spontaneous or not. And we typically use it when, one driving force is saying, yes, the reaction should go, and one driving force is saying, no, it shouldn't. And so to calculate delta G, it is equal to delta H minus T delta S. Delta H is the enthalpy of the system, T is the temperature, and then delta S is the entropy of the system. So this, again, is just calculated. It cannot be measured in a lab. It's completely made up. When delta G is negative, that means the reaction is going to occur without outside intervention. That means the reaction is spontaneous or thermodynamically favorable. So delta G is negative. That means it is spontaneous or thermodynamically favorable, which means the reaction is going to occur, it is product favored. So naturally it will occur. Again, it doesn't mean that it's going to occur fast, but eventually it's going to occur that we favor the products more than the reactants. If delta G is negative, then it's not spontaneous or not thermodynamically favorable. which means it's better to go the other way. It is reactant favored. The reverse reaction is favored, right? So it's reactant favored. We'd rather have reactants than we do products. If delta G is 0, then that means we are at equilibrium. So based on what we just talked about, what is the relationship between delta G and K, the equilibrium constant? Well, if delta G is negative, that means it's product favored, which means K is higher than 1. If delta G is positive, which means it's not favored, it's reactant favored, that means K is less than 1, right? So let's write that down. When delta G is positive, K is less than 1. When delta G is negative, K is greater than 1. And when delta G is equal to 0, K is going to equal to 1. So let's look at this process here, which is the melting of water, the melting of ice, right? And we're going to check whether it's thermodynamically favorable or spontaneous at the following temperatures. We have negative 10 Celsius, 0 Celsius, and positive 10 Celsius. You probably can figure this out right now, right? Because you know what temperature water melts at, right? But we're actually going to do the calculations and see. Now, any phase change, just so you know, is always going to be favored by one of the forces and not the other. Let's look at this one. So going from solid to liquid, let's look at entropy, delta S. What do you think? Is that entropy driven? Yes, it is. Going from a solid, which is highly organized, to a liquid, which is a little bit more disordered, that means delta S is positive and it is favored. And if you look at this, delta S is positive, right? So that checks. How about delta H? Well, in order for a solid to become a liquid, which has higher energy, the system has to absorb energy to get there, and so that would be endothermic. Your delta H is positive. That is not favored. So this process is favored by entropy, but not by enthalpy. It is entropy driven, but not enthalpy driven. So it's favored by one and not the other, so we're going to calculate delta G and figure out if it's going to be spontaneous or not. So we're going to say delta G is equal to delta H minus T delta S. And so delta H here is 6.03 kilojoules per mole minus my temperature is negative 10 Celsius, which is 263 Kelvin. My delta S, watch out, this is in joules per mole Kelvin, this is in kilojoules. So you got to convert one or the other. Since I already wrote the kilojoules, I'm going to go ahead and convert my delta S to kilojoules per mole Kelvin. So I'm going to divide by 1,000, so that would be 0.0221 kilojoules per mole Kelvin. Okay, we're going to do the same thing here. Delta G is equal to delta H minus T delta S again. So 6.03 kilojoules per mole minus my 0 Celsius would be 273 Kelvin. So the only difference here is the temperature. Same thing here. So 6.03 kilojoules per mole minus 283 Kelvin. And we'll go ahead and calculate that. If you have a calculator, punch it in. This one gives you positive 0.217 kilojoules per mole. By the way, the units for Gibbs free energy is kilojoules per mole. This is kilojoules per mole, and then this is Kelvin times kilojoules per mole Kelvin. So the Kelvin here crosses out with the Kelvin here, and you get kilojoules per mole. This one gives you negative 0.0033 kilojoules per mole. And this one gives you negative 0.224 kilojoules per mole. So let's look at these values and decide, is this process thermodynamically favorable at these temperatures? So here, it's a positive value, so that means it's not spontaneous. Not thermodynamically favorable. I'm going to use spontaneous because it's just shorter to write, but on the AP exam, you want to use thermodynamically favorable. College Board prefers that term. So we know that, right? At negative 10, water is not going to melt, or ice is not going to melt. So we knew that that's not spontaneous, right? Let's look at 10 Celsius. 10 Celsius, our value is negative. So that means it's spontaneous. Remember, when delta G is negative, that's spontaneous. When delta G is positive, that's not spontaneous. And so we also knew that makes sense. 10 Celsius, water should melt. How about at 0 Celsius? Look at the number. It's so small. It's almost 0. And so here we're at equilibrium, which makes sense. At 0 Celsius, you have equilibrium between freezing and melting of water. So what is deciding here when you have two fighting forces? One says go, one says no. What decides between them? Well, what's the only difference between these three? It's the temperature. And so the temperature decides when delta H and delta S disagree. It depends on the temperature. At some temperatures, it's going to be spontaneous. At other temperatures, it's not going to be spontaneous. So let's look at how the temperature affects it. So again, the equation is delta G is equal to delta H minus T delta S. Notice that the temperature is multiplied by the delta S, right? So the higher the temperature, the higher that delta S value becomes. And so higher temperature is going to make delta S win, right? Because you have the delta H term and then you have the T delta S term. And if they are disagreeing, then at high temperatures, we're going to make this bigger than the delta H. And so we're going to make the delta S, whatever it says, win. At lower temperatures, very small temperatures, it's going to make this term small. And so you're going to make the delta H win. So let's look at the 4 different scenarios that we had talked about. Delta S positive, delta H positive, negative. So delta H is positive, that is favored by entropy. Delta H is negative, that is favored by enthalpy. It's favored by both. It's enthalpy and entropy driven. Delta G is always going to be a negative value. If you plug in a positive here and a negative here, and you calculate it, no matter what the numbers are, delta G is always going to be negative, and so it's always going to be spontaneous or thermodynamically favored. Let's look at the last scenario here. Delta S negative, that's not favored. Delta H positive, that's not favored. It's neither entropy or enthalpy driven. If you plug a negative value here and a positive value here, no matter what the numbers are, delta G is always going to be positive, and it's never going to be spontaneous under any conditions. Okay, now let's look at when they're both positive or both negative. Let's start with this one. Delta S is positive, that's good. Delta H is positive, that's not good. So this one is entropy driven, but not enthalpy driven. So entropy is saying go, enthalpy is saying nope. And so let's see when this value is going to be negative. Well, if it's favored by entropy, then if we make this value bigger to overcome the delta H, then it's going to be spontaneous. And so it's going to be spontaneous at high temperatures because then the T delta S value is going to be bigger. And so this type of reaction would be spontaneous only at very high temperatures. And you can actually calculate what that high temperature is. We'll do that a little bit later. If delta S is negative, so that means not favored by entropy. Delta H is negative, that means it's favored by enthalpy. So now they're fighting again. Delta H is saying the reaction should go. Delta S is saying no. And so when would the reaction be spontaneous? When would delta H win? Because we want delta H to win here because it says it's favored. And so that's when this term is small, and so we want the temperature to be low so that delta H wins. And so these types of reactions would only be spontaneous at low temperatures. So you need to be able to look at whether delta H and delta S are positive or negative and be able to tell, are these reactions always going to be spontaneous, never going to be spontaneous, or sometimes they'll be spontaneous, and if it's sometimes, when will they be spontaneous, at high or low temperatures? Okay, let's look at this here. It says, given the following thermodynamic values, determine whether each reaction is enthalpy or entropy driven, and if the reaction is thermodynamically favorable, meaning it's spontaneous. So let's look at the first reaction. They give us delta H, delta S, and temperature in Kelvin. So we're going to say delta G is equal to delta H minus T delta S. Let's start with the first one. Delta H is positive. That means it's not favored by enthalpy. Delta S is positive. That means it is favored. And so this is entropy driven. And at that specific temperature, let's see if it is thermodynamically favorable or not. So delta G is going to be delta H, which is 40 kilojoules minus temperature is 130 Kelvin, and delta S is 0.3. Remember, usually they give us this in kilojoules and this is in joules, so you got to convert one of them. And so when you do this calculation, you get positive 1 kilojoule. And so this is not spontaneous, not thermodynamically favorable. Let's look at the next one. This is positive again, so that's not favored. Delta S is positive, that's still favored, and so it's still entropy driven, not enthalpy driven. So we got to calculate delta G. So 40 kilojoules again minus, we changed the temperature here, and we're at a higher temperature, so we have a chance here. We get negative 5 kilojoules. And so this is spontaneous, thermodynamically favorable. Let's look at the next one. Delta H is positive, that's not favored. Delta S is negative, that's also not favored. It's neither entropy or enthalpy driven. And so no need for a calculation. It's never going to be spontaneous because it's not favored by either. If they ask you to calculate it, then go for it. But if they're just asking if it's thermodynamically favorable, you don't need to do a calculation. You're going to get a delta G that's always positive with these numbers. Okay, last one. Delta H is negative. That is favorable. Delta S is negative. That's not favored. And so since it's favored by one and not the other, we want to go ahead and calculate the delta G here. So this is enthalpy driven, not entropy driven. Delta G is negative 40 kilojoules minus 150 Kelvin times negative 0.3 kilojoules per Kelvin. Go ahead and calculate it. You get plus 5 kilojoules, and so this is not spontaneous at that temperature. Okay, so if your delta G is negative, that means the reaction will naturally occur. If your delta G is positive, that means the reaction will not naturally occur. So does that mean the reaction can never occur? Well, not under natural conditions, but you can make the reaction go. You can force it to go. And so the only way that you can force it to go is by applying some kind of outside force, and these outside forces can include either using electricity, like water decomposition is not favorable, and so we got to use electricity to do it, electrolysis. So electricity makes a non-spontaneous reaction go. Or using light energy or some sort of lots of energy like photosynthesis. Photosynthesis is not favorable, and so we use light to get it to go. Or you can couple reactions. So coupling means you do two reactions together. And so if you couple two reactions where one is not favorable and one is really, really super favorable, then together the process might have an overall negative delta G, and then your reaction could occur. So these are the three things that we could do to a reaction that has a positive delta G that is normally not spontaneous to get the reaction to go.